Okay, today we're going to talk about standing waves. And standing waves are a different kind of wave than we've talked about. So we've seen wave pulses and we've seen traveling waves. But a standing wave is a very particular type of wave that occurs when we have more than one wave in the same medium. So the first question we have to answer is, well, how does that happen? How do you have more than one wave in the same medium? And the answer is pretty simple. So take a look at the picture we've got here. We've got a wave, and let's say this pink line is the wave, right? There's a string, and there's just that wave pulse. And when I hit run, we're going to see that the wave is going to propagate to the right, and it's going to hit this fixed end, which looks like a dashed line here. We call this the incident wave. This is the incoming wave, okay? What's going to happen when the wave hits that fixed end is it's going to reflect back. I'm going to hit pause there, and then we're going to see that we have a reflected wave that comes back. And you can notice a couple of things. I'm going to let this run a little bit. So the incident wave is going towards, it reflects off the boundary there, and it goes back. So we have an incident wave and a reflected wave. Now, because this is just a pulse, all we see is really one pulse at a time. And we notice something at the free end. This line is dotted because it's a free end. So it's basically a loose end. You can see here that the pink line, the medium, the rope, is free to go up or down as it so chooses. If I were to pause, though, and go ahead and hit reset and change that free end to a fixed end, when I run the simulation again, we're going to see that when the wave reflects from the boundary, which is now a fixed boundary, that's why it's a solid line, when the wave reflects, it actually drops down. So instead of having a crest, we have a trough. Okay, so the first thing we have to understand is that when we hit a fixed boundary, our wave is going to invert. And when we hit a free boundary, the wave is going to stay on the same side. But either way, we're going to have an incident wave going towards the boundary and a reflected wave going back from the boundary. So now let's take a look at another simulation. And I'm going to go ahead and reset this and start it. And now our wave, we still have a wave and a rope, and I've left it as a fixed end. And we can see that the individual particles of the rope are going up and down, represented by those red lines. So the wave is traveling from left to right, and that each of the individual particles are going up and down. So this is a transverse wave. And we can see that it's moving pretty slow, but eventually it's going to get to this fixed end. So this is the incident wave, the incoming wave. And when it hits the end, it's going to drop down, and we're going to have a reflected wave. And we can see that in the blue. Now I could turn the incident wave or the resultant wave off here. And I can see now that every place that I have red and blue, I have two waves. I have an incident wave and I have a reflected wave. And these waves are going to do what's called interfering, because the interference results when we have two waves occupying the same space in the same medium. So what we would see, though, is not these red and blue, because if I pause this for a second and looked at it, how could the rope be going up and down at the same time? That's obviously not possible. So I'm going to turn on the resultant wave, and I reset it. That's too bad. And I'm going to let it go again. And we're not going to go in slow motion or anything, but we're going to see that the incident wave, when it hits there, is going to reflect. We're going to get that reflected wave, and then what we're going to see is a standing wave. Now we have two different types of interference. We have constructive interference, and think about what the word constructive means. It means that you're constructing something, like you're building something up. And we have destructive interference, which means that something is being destroyed. So when we get to the point where we're going to have our incident wave interfering with our reflected wave, we're going to be able to see the resultant wave, and it's the result of this constructive and this destructive interference. So I'm going to turn off our incident and reflected wave, and we're just going to see the resultant wave. So you can see all the way in the left, the waves aren't interfering yet. I've just got an incident wave. But as the reflecting wave, gets further and further to the left, we're getting this standing wave pattern. And it looks like there's no wave traveling to the right and there's no wave traveling to the left. It looks like the material is just going up and down repeatedly. This is a standing wave. If I were to turn on the incident wave and turn off the resulting wave, this looks like a traveling wave. I can actually see the wave going from left to right. And if I were to turn on only the reflecting wave, I can see that wave is going from right to left. And when I turn on the resultant, it doesn't look like it's traveling at all. It looks like the medium is just going up and down. And we can see these spots on the the horizontal line there that horizontal line represents the undisturbed rope, we can see those ends. Those are called nodes, and that's a location where there is no motion, right? It's always still, so that's a location of destructive interference. The rope there is never moving. And then we have these areas where we've marked A, that stands for antinodes, and we're going to see that that is the location where we get the most constructive interference, and that's the most displacement we're going to see in the rope. So I know that we went kind of fast through this. This is just kind of a nice view. We're going to make some of these waves in class, and we're also going to study these quite a bit. So we're going to take some notes with this as well. So let's go ahead and take some notes here. So right at the top here, I'm going to talk about that how a standing wave is comprised of an incident wave and a reflected wave interfering in the same medium. And that we're going to get constructive and destructive interference as a result of these two waves. This occurs because when a wave reaches a boundary, and if the wave reaches a fixed boundary, which means the medium can't move, so it's basically clamped down, the wave is going to flip to the other side of its equilibrium position. But if the wave hits a free, we call this a free or a loose end, when the wave reflects, okay, the wave is going to reflect, but remain on the same side. And we're going to see this type of behavior in all kinds of waves, including sound waves. So we're going to do an echo lab as long as we have time. And we're going to see how waves reflect. Sound waves can reflect off of a building and come back to us. Okay, so they reflect off of surfaces. Absolutely they can. So they can reflect off a building wall. And we will hear an echo. Most of the waves, the standing waves we're going to look at, are going to be transverse standing waves. So for instance, we're going to make some, and we can make them in a rope or a spring. So what happens is that the incident wave reaches the boundary and reflects back. The incident wave and the reflected wave interfere to create a standing wave pattern. We're going to see these patterns, and there's a couple of things to keep in mind. First of all, you can't create a standing wave at just any frequency that you choose. So we're gonna do a lab, and you're gonna create some standing waves, and you're gonna find that you have to have the right rhythm, and you have to be moving the rope at the correct frequency, or you won't get a standing wave. The incident wave and the reflected wave have to interfere just perfectly to get a standing wave. And this only happens at certain frequencies. Okay, so we're gonna see that, and then we're gonna see that a bunch of different patterns can emerge. Okay, so in class, we're gonna make a standing wave with 3 loops, and what that's going to look like is I'm going to have, let's say, a rope, and I'm going to show the undisturbed rope. So this might be our undisturbed rope. That's not a very good straight line. Unfortunately, the app is not Notability. It doesn't let me make these very easily. And then what we do is we're going to put a standing wave, and there's going to be 3 loops. So this is going to be one loop right here. The second loop is going to be right here. And the third loop is going to be right here, and they should be even. I went a little long there, so I'll just go ahead and draw this line a little longer. And we can see several things here. Okay, we can see that there's nodes right here, right here, right here, and right here. So those are the nodes. And then we can see at these other locations here, for instance, right here, and right here, those are the antinodes. So we can label our nodes with an N and our antinodes with an A. So that's the pattern that we'll see in class. And if we want to highlight just one full wavelength, so a wavelength is a crest and a trough. So this right here, so one crest and one trough, is one wavelength. So let's say that we know from some method, if we know that the wave speed of this medium happens to be 12 meters per second, and we want to figure out the frequency made by this standing wave pattern. Well, to figure out the frequency, if we know the velocity, we're going to need the wavelength. So that's why in number 1 we say, okay, well, the length of this rope is 6 meters long. That means that this distance from here all the way to here is 6 meters. Well, that's true, but how big is one wavelength? And you might be able to see pretty quickly that one wavelength going from here to here, if the full distance is 6 meters, this distance from here to here must just be 4 meters. But how would you get that if you don't see that? So here's how I do it. I take a look and I say, well, okay, I know from the start of the length to the end of the length, I can see how many loops there are. There are 3 loops, 1, 2, 3. Well, how many wavelengths is that? That's one wavelength plus 1/2 of a wavelength. That means I have that 1.5 wavelengths is the same as the 6 meters, right? Because the distance from here, where I see that first end, to here, the last end, is 6 meters. Well, the distance from this first end to the last end is also 1.5 wavelengths. So I can set those equal to each other and divide by 1.5, divide by 1.5. I can see that the wavelength must be equal to 4 meters. Once I have that, I can use my V is equal to lambda times F equation, and I see that 12 meters per second is equal to 4 meters times frequency. The frequency, therefore, must be equal to 3 hertz. So we can draw lots of different standing wave patterns in our rope, and there's just a couple rules we have to remember to follow. First rule is that anytime there's a free end, so if we have a free end, we know there must be an antinode at that free end. The second rule is that if we have a fixed end, there must be a node at that end. So when we ask you to draw the first 4 standing wave patterns we can make in a stretched rope, we're going to assume that both ends of the rope are fixed. So one end is fixed maybe at the table and the other end is fixed at my hand. And we're going to say here, we're going to assume that the stretch distance is 60 meters. That's a really long rope. And then we're going to calculate the wavelength for a couple of waves. So let's take a look at the first standing wave pattern we can make. And this should look pretty familiar. It kind of almost looks like a jump rope. So I'm going to follow my rules, and I'm going to say, okay, well, my first rule is that at a fixed end I have a node. That means I can draw the most simple standing wave like this, where I've got a node here and a node here, and I know this length is 60 meters. And then I wonder, how many wavelengths is that? It's not one full wavelength. It's part of a wavelength. And I know that it's 1/2 of the wavelength because it's one full loop, and one loop is half a wavelength. So I know that the distance from one node to the next node is 60 meters. It's also half a wavelength, so I can set those equal to each other. And I can say that 1/2 lambda equals 60 meters. And when I solve that, I see lambda must be 120 meters. I'm going to draw the next possible standing wave, and I can see that I'm going to simply add in one node in the middle. So I'm going to have 1, 2 loops. Therefore, I'll have 3 nodes. When I look at this, I know it's still 60 meters, but it's 2 loops now. So instead of being half a wavelength, this is a full wavelength. Well, since it's one full wavelength, that must also equal 60 meters. The next standing wave I can get is going to be 3 loops. 1, 2, 3. Well, it's still 60 meters. But how many wavelengths do I have now? Well, 3 loops means I have 3 halves of a wavelength. That's going to equal 60 meters. So when I solve for my lambda, I should see that I get 40 meters for one wavelength, which makes sense because I've got 1.5 wavelengths in there, so I can see that the wavelengths are getting smaller and smaller. I'm going to go ahead and I'm going to do my 4 loops. 1, 2, 3, 4. And I can see now I've got 1, 2, 3, 4, 5 nodes. And if I look at how many wavelengths I have, I can see that I have half a wavelength. Then I've got 1 wavelength, 1.5 wavelengths, and then I've got 2 wavelengths. So I can see that I increased by another half of a wavelength. So I get 4 halves of lambda, or 2 lambda, is equal to 60 meters. So lambda must be equal to 30 meters. And I could keep going. And why don't we do one more, just so you see it. And then instead of drawing 1, 2, 3, 4 loops, I'm going to draw 5 loops. 1, 2, 3, 4, 5. It's still only 60 meters. But I've got 1, 2, 3, 4, 5, 6 nodes. And if I count how many wavelengths I have, let's see, I've got half, 1, 1/2, 2, 2 halves. So 2.5 lambda is equal to 60 meters. And now I can solve for that. And I can see that lambda equals 24 meters. So we're going to go ahead and we're going to do a lab like this in class. You're going to have to remember how to add up the number of loops, how you get the number of wavelengths from the number of loops, and then we're going to get some velocity measurements from that.